All right. So as I was saying, these the planets that are in some cases a little more massive than Jupiter, actually, so some a lot more massive than Jupiter, and they find themselves really close to their host stars. They have been dubbed hot Jupiters. All right, so that's just pretty soon we're going to talk about what are called um, super Earths as well. Now we don't think, remember, we think that our Jupiter, of course, moved in the early parts of the solar system, and we think that that might be what's going on with these hot Jupiters. We don't think these Jupiter-sized worlds could form that close to their star, where their period is only like a day or a couple of days or something like that. I mean, it's just there's not the gaseous material to form. You need to be way out, um, away from away from your star to form like that. At least that's the theory right now. This is another. So there's lots of worlds. Just to let you know, there's over 5,000 planets that have been confirmed, right, around other stars. So just about every star within, you know, so here, the Milky Way. Okay, our galaxy, and that's the other thing is we only see stars or planets around stars within the Milky Way. I want everybody to understand that. You can't see, you can't detect. We don't have that ability to detect planets around stars in other galaxies. Although, if there's stars, if there's planets around stars within our galaxy, we certainly expect there to be planets around stars in other galaxies. I mean, that there's, the same laws of physics apply. All right. So anyhow, lots and, so here's the thing. To confirm it, you have to see several. You have to have several uh, times the planet going around its host star. So several of its years, right? It's not a so some of them like this one, a year for it. What would be considered a year for this particular world would be 4.2 of our days, right? Like 4.2 times 24 hours. That's how long it takes to go around its star. So that would be I mean, what we generally do in astronomy is we talk about a year being 365.24 days, right? Because that's the amount of time it takes the Earth to go around the sun. And an hour is an hour. A day is a day. Is 24 hours, and a second is a second. So what we do is we compare, Earth time, the amount of time it takes these worlds to go around their star, and in terms of numbers that we can understand. All right, so there are some worlds that are up to anywhere from about 2 to about 10 times the mass of Earth. Those have been called super Earths. So they have found some Earth-sized worlds, but more than usual, we find either Jupiter-sized, or in fact, most of the exoplanets that we've been finding are Neptune-sized worlds. Just to give you a sense, you'll see that in just a little bit. All right, so this radial method has shown us over. I mean, this slide is probably a few years old, so it's shown us probably over 1,000 planets, or we've detected over 1,000 planets. All right, here comes the next method. All right, now this method is so I got to tell you a little something about Einstein. All right, and Einstein's theory of general relativity. So the general theory of relativity says that light, well, here, it's the general theory of relativity says that um, that gravity is really just curved space and time. So any massive object like a star or a planet will bend space itself. All right. So, and by the way, that's just been verified time and time again, right? 1915, Einstein comes up with this theory. The theory is almost, it's indistinguishable from Isaac Newton's theory of gravity for, ordinary things like space travel, like if we want to go to the moon or go to Mars or something like that. You can use Newton's theory of gravity. It works the same. It's only when you get in extreme situations that you actually get to use or need Einstein's theory of general relativity. All right, so here's the situation. All right. So again, and by the way, we've only found about 100 exoplanets with this method. All right. So it's not very fruitful. Okay. It's just not at all very fruitful. We found a lot more planets using the radial method, also known as the wobble method. All right. So here's how it goes. Light comes along from some distant star, much further distant star, passes by a star that's between us and that distant star. So the only thing that's important about this distant star is that it's providing us with some light. And then as it passes by this star, so in other words, it's got to line up exactly, right? Like it's got to line up perfectly. And when it does so, the light will bend. And what happens is if the planet is on one side, it will bend a little bit more because, that's more mass. If the planet is on the other side, it will bend more on the other side. So the amount of bending on either one side or the other, from a line that you draw straight from the Earth, if there's more bending on this side, that means the planet is over here. Then over time you're going to see light bend on this side a little bit more, and you can actually measure the period, and you can measure the size of the planet. Just by timing it, how long does it take this gravitational lensing to repeat itself? So, like I said, this is not very fruitful. Only about 100 exoplanets been found this way. But it does take a lot of telescope time, which is very valuable. There's lots of astronomers competing to get telescope time all the time. You got to use rather large telescopes, professional telescopes. A backyard telescope is not going to help you with something like this. All right, so then we get to the most fruitful method of finding exoplanets, and this is the one that's used all the time. All right, so it's called the transit method. All right, so this is how it works, and usually, by the way, there's been two space telescopes that have used the transit method. One, which doesn't work anymore, was called the Kepler satellite. The Kepler satellite was operational for about 4 years. It discovered thousands upon thousands of candidate exoplanets, and then so we've confirmed. Confirmed just means that you've seen several orbits, several complete orbits of these things, and that confirms it as a true exoplanet. At any rate, so the Kepler satellite was monitoring over 1,500 stars within our galaxy, and then there's another satellite called the more modern one is called TESS, TESS. It's like the Transit Exoplanet Survey Satellite or something like that. I forget what it stands for, but it's something like that. It's called TESS, and TESS is currently operational. It's finding planets all the time. All right, so here's how it goes. All right, are you ready? Um, so the planet now you got it. The planet has to be passing in front of its star, or at least part of it has to pass in front of its star with respect to us. It doesn't always line up across the middle of the star, right? It could be going this way, or it could be just a little piece of this. But at any rate, it blocks a little bit of the light. Now, so there's a tiny little dip in the light of the star, right? To give you a sense of how small of a dip this is, and this is why this was so difficult to detect for a long, long time until we got the technology to be able to do this, is imagine, so let's say you're looking at some large wall, okay? And in that wall, there are 10,000 100-watt light bulbs, right? So that way you have them all on, let's say. You have all 10,000 100-watt light bulbs on. That would be a lot of light, right? I mean, anybody, and you can imagine that that's a lot of, an incredible amount of light. Now, this dip that we're talking about is as though of those 10,000 light bulbs, somebody turns one light bulb on and off. That's the kind of dip that we can now detect. That's the idea. All right, so that was the mission of Kepler, which is a satellite that doesn't work anymore. But then of course they launched the satellite called TESS, and that is that has been extremely fruitful. Now, of course, if a planet is doing this, if it's going perpendicular to our line of sight, we're never ever going to see a transit. It's got to actually pass across its star for us to see this. All right, so now what I want to do is talk about what's called the habitable zone. So there is this thing called the habitable zone. Where, okay, so it's a really simple idea. Okay, so this is just showing you where the habitable zone is when you look at different stars, different distances. So different stars have different amounts of heat, right? There are really large stars that produce tremendous amounts of heat. There are really small stars. In fact, that's the vast majority of stars in the Milky Way are much smaller than our sun. Right now, what we mean by the Goldilocks zone, or sorry, the habitable zone, it's also sometimes called the Goldilocks zone, is when a world is too close to its host planet um, for liquid water to exist. Right? It's really, that's the key, is liquid water. So if it's too close, the planet's going to be too hot, and all the water will vaporize, and so you won't have any liquid water. If it's too far, that's outside the habitable zone, then water will freeze. Now you can have some freezing, you can have some frozen water, just like the Earth has frozen water, but the majority of water on the Earth is in liquid form. All right, so that's this idea of the habitable zone, and of course, water is the only form of life that we know of course, is the life on Earth, and all forms of life on Earth need water. All right, so that is what we've been that's the stuff that we've been detecting. Like I said, there's more than 5,000 planets that have been detected, mostly using the transit method. There have been some super Earths that have been discovered, but the big surprise was having Jupiter-sized worlds really close to their host stars. We can use this to find mass. We can figure out density. Yeah, that's the chapter. That's chapter 11. All right, I finished just in time. That was actually pretty good timing. All right, so I'm going to do some. I'm going to yeah. Well, that's the end of the chapter.